A little bit of technical adjustments here. We're just about ready to start. Hello, everybody.
Okay. So we have Mark dialing in to join us because we will be demonstrating some of the tools that he made connected to Ceptr. Welcome. So how about take the poll?
Great. So let's see if what we want to do is just have a little poll to start out with to see a little bit about the folks who are signed on here. Well, first of all, thanks for being here. I'm Eric. This is Arthur. Say hi.
Hello.
What we're doing today is the dry run of a webinar that we're going to be hosting tomorrow with MIT KIT. So we're grateful to you for being here on this dress rehearsal. So we'll have some of the dress rehearsal qualities of a little bit of sloppiness, and we look forward to your feedback on that so that we can prepare better for tomorrow's event. So I think one of the things we wanted to start out with is just a poll. If you could type into the chat, give a rating of 1 to 5, 5 being the most, 1 being the least, of how techy you are, how geeky you feel yourself to be, because this this whole webinar is fairly technical, and we want to just have a sense from the audience where they are, how they self-rate in that. So, Arthur, can you bring up the chat so we can see that too?
Hey, Arthur, in the image of the broadcast, I'm seeing me, not you guys. So you have to select in the film stream your video, not me.
How many people do we have online? Okay, we've got 8 viewers right now. Okay, gotcha. Great.
So far, it's 2 minutes. We're just starting. So
a few minutes in.
Maybe we should start over with us, actually.
Yes, I think you should start over. Yes.
All right, your turn. Do it again.
There is a delay of 2 minutes.
So this is our first time hosting a Google Hangout. Fernanda has done all of the running behind the scenes before, so we already messed up by having her camera selected while we were talking. So here we are learning the tools. So welcome to the Ceptr demonstration. There's a lot of cool things we've been building, and we're happy to have a chance to actually show them off a little bit. Unfortunately, Ceptr is a very geeky, low-level thing that...
or fortunately, depending on how you look at that.
Well, it makes it challenging to show things. So we created some additional interfaces and ways of being able to visualize, to see what's happening under the hood. It still doesn't exactly have like a user interface. So Eric was just taking a little bit of a poll, and I'm not seeing any responses. So I'm not sure if we have the right chat or if you have to see them on the event page. Yeah, I think maybe you have to see them on the event page.
Well, let me bring that up over here.
Okay.
Okay, in the event page, yeah, you can, if you click the question and answers, you will see the people.
Q&A, here they are. So, Eric asked on a 1 to 10 scale for you to rate yourself. You should.
Yep.
For you to rate your geekiness, so we get a sense of who we're dealing with and how geeky to have this conversation. Tomorrow's call with MIT, we're definitely planning to have you.
There we go. It's in the Q&A section. I see it.
Christopher Allen is saying he's not seeing the chat box. There's a bunch of people. Hayes is saying they have no chat box.
So what you do is you click on the question and answer page. It looks like how you get to do that. There's on the top of the Hangout, there is a little there's a place to answer questions. So I guess now to see this is not there isn't a regular Google Hangouts chat because we're doing it as a Hangout on air. So
right, it's not a Hangout chat box. It's a Q&A thing you can access from the event screen. So hopefully that will.
Not very helpful. Well, why don't we just dive in? Our poll was a failure. Now we'll move on to the next thing. I think
let's start.
So are you going to go ahead and share the screen?
Yes. So Fernanda's saying she can't do anything as she's not a moderator. But I thought we made her one. This is definitely a first time for us on these tools. Okay, so let's screen share. No. This. And when that goes into present mode, does it go full screen? No. It disappears. Awesome. Oh, this is a great start.
I think present to everyone. You have to click present to everyone, and then it'll work.
But it's not showing in the screen.
All right, we'll try again. So hit. Okay, yeah.
Let's try putting it on the same computer. Aha, that makes a difference.
But no, you still need to go to the in present mode, and it's not working. But you can't tell whether it's not showing up. It shows up blank when it goes that way. I'm seeing it over here.
Okay.
So you're just gonna have to expand this. You're gonna have to walk through it and figure this one out.
Awesome.
There it is. And also you got to bring it back to the top.
No,
you're on expectations. You need to.
You're just seeing a lag.
Okay. There we go.
Okay. So we'll try presenting this way. So this is. Let's resize it. Hope to make it. Okay. Now we're maybe in a mode that we can actually show the presentation. All right. And Mark was supposed to be on the call with us, but along with the other technical difficulties we're having, we seem to not be able to get him dialed in. And so, unfortunately, he won't be able to speak during his portion. So some context and background. Why Ceptr? We built Ceptr because when we were working on the MetaCurrency project, we discovered that to build most of the things that we wanted for truly distributed and decentralized systems that were interoperable and resilient, that were highly composable and meaningful, semantic, that we needed a lot more underlying infrastructure that didn't exist. And the current efforts like blockchain and APIs and RDF were falling far short of the kind of composability and resilience that we wanted. And so it looked like we had to kind of go deeper back to the drawing board. And then we had some breakthroughs in that process that gave us more confidence to actually kind of go back and build everything from a low level. So Ceptr is actually pretty low-level infrastructure without a lot of user interface. And so we built some visualization tools to make some of the internals visible just for this demo. And we're going to start actually with a demo of Hope, which is a user interface that Mark Clifton has built in C# on the Ceptr principles. This portion of it isn't actually built on Ceptr. There are parts where he has built things from our code in GitHub, but HOPE stands for the Higher Order Programming Environment, and he has taken these patterns that we're using and done some pretty cool things with it. So hopefully...
This is a short introduction of the Higher Order Programming Environment, or HOPE. With HOPE, we use both specialized and general-purpose autonomous computing units, called receptors, to compose rich data transformations and visualizations. All data is semantic. It carries both value and structural meaning. Receptors, like cells, absorb specific semantic data, perform computations on the data, and release the computational results as semantic data into the inter-receptor space, where other receptors process the new semantic data. Membranes define bidirectional permeability within receptor groups to control data flow and create computational islands. The demo you are about to see illustrates some of these concepts. We will utilize several different receptors to extract specific information from a website and to interact with the website's information in different ways than originally intended. The website we'll be working with is NASA's Astronomy Post of the Day, APOD website. So let's get started. First, we will select the APOD receptor and add it to the surface. This receptor will query the astronomy post for a specific date, but it depends on a general-purpose HTML scraper to extract the HTML. Once it gets the HTML, it extracts some content, such as the image, the title, and description, and issues this as a web image semantic instance. Let's add a signal creator receptor so that we can feed dates to the APOD receptor. Now, this is a general purpose receptor in the sense that we can select the semantic type that we want to create, and the UI generates the entry fields dynamically for us. Now, it doesn't really know that a date could be selected with a date control, so it just gives us text boxes for the different value types within the date semantic type. So I'm going to put in Valentine's Day of 2014, and we'll click on Create. Now notice here, we have a connection now between the signal creator and the APOD receptor, and that the semantic type that is being conveyed from the signal creator receptor to the APOD receptor, that semantic type is date, because that is, after all, what we selected here in the dialog, and APOD is receptive to date semantic types. Now let's add the web page scraper receptor, and you're going to see something interesting. You'll notice how there's this interaction now between APOD and the web scraper. What's happening here is that APOD, once it gets the scraped HTML, it's actually generating a web image semantic type instance. That web image, as we noted over here, contains a URL, and because receptors can also respond to subtypes within a semantic type instance, the web page scraper is actually responding to the URL in the web image instance as well. We don't really want this behavior, so we're going to create a membrane around the web page scraper, and we're going to configure it so that we are permeable only to the URL as a root semantic type, not as a subtype. And we also have an outbound permeability for the web page image. I'm sorry, for the web page HTML. And now we have stopped that feedback loop. Now let's get to the fun part. We're going to add an image viewer. And that popped up a separate viewing window. Now that my screen space is limited here in this video, so we're going to have to switch back and forth between things. We'll put a membrane around the image viewer as well to constrict its data transfer of semantic types as well. So what we're interested in here is a web image, and there we go. Now you can see over here, we have this beautiful picture. Now let's quickly add a couple other receptors. One is going to be a text display receptor for the description. So I'll add that, and we want to restrict it specifically to the description semantic type instance. And then I'm going to do something interesting. I'm going to add a web page viewer receptor. And what I want to do here is take just the title. So we're going to say we're receptive, permeable, in for the title. And I'm going to configure this receptor for doing a Google search on the title itself. So we're going to add this little URL with this token, it's called search, which takes the title, replaces the text in the title with this token, and performs a Google search. So now let's just re-trigger this whole thing again. And move this out of the way. We can see the semantic type instances being moved about to the different receptors. And now here is the result. We have these three different tabs. We can reorganize this a little bit. So let's move the text over here. And let's move the image down below the text. And here's our Google search, where we can now see things that relate to light from the heart. We can look at, for example, another date. There go the different semantic type instances. And here's the result. So, in conclusion, this really is just a teaser of how you can use Hope to create dynamic and rich applications. And I encourage you to visit the higherorderprogramming.com website for more examples, articles, and videos. Thank you for watching. This is a short introduction.
Okay. Well, I think I have to declare the screen sharing part of this a bit of a failure. Unfortunately, when I go to full screen presentation mode, it stops sharing it altogether, and I think it's very hard to see the video in the smaller form that it's in at the moment. So using a Prezi along with Hangout seems to be not the best plan.
It's all right.
In any case, so sorry, going back and forth between the controls. So hopefully you at least got a sense of what receptor-based computing can look like there, in terms of how easy it is to assemble things and have them interact with each other and have signals go back and forth and listen for particular types of information on signals. So Ceptr is structured that way, except there's some differences in how we have things structured than how Mark built it in Hope, in that all receptors have membranes, and they can be organized fractally. They can be built inside of each other. So you can have really big ones, like the virtual machine host that hosts all the receptors on a particular machine to really small ones, like that almost are like a specialized function, and everything in between. So receptors become a unit that you can use to compose all of your computing. So now let's actually go into understanding the rest of Ceptr. So you've already got this first part. Ceptr's built out of fractal receptors, and you should feel free to chime in at any time. Receptors receive and send signals, and there's an underlying pattern of this carrier signal protocol that we one of the breakthroughs we had was identifying how that repeats at every level, so that if you make a receptor be able to receive on a particular carrier, then it can receive any type of signal. And if you make the protocols actually pluggable, then receptors can learn how to process signals after they've received them by installing the right protocol. And in any case, so receptors are bound to particular external carriers, and it reminds me a lot of, like, in hormones in the body, how they're shaped in particular ways to bond with other patterns. And so when you instantiate a receptor, you bond it that way. A receptor is a really lightweight virtual machine, and it's also wed to a slice of a data engine for persistence. So it's a virtual machine plus database, sort of. In short, receptors manage coherence. So they manage their membranes, what can come in, what can go out, and any transformations of things in that process as they might be translated coming in or translated going out. They store their state, both ephemeral memory and persistent data store. They transform their state by running code. They escape data, and we're not going to talk about this much today, but it's one of the interesting things for the relational intelligence is that they actually index collections of data that they have and can compute things on relationships between different instances of data. And then here's one of the really cool things is that they sync with their other instances. So you can have an instance of something, like a Bitcoin-like currency, and it synchronizes with the other instances. And so this is kind of there's a few different ways that this works, but it uses kind of a holographic storage model, a little bit like a distributed hash table scenario, and provides distributed Byzantine fault tolerance. So so here's one of the weird things to understand about Ceptr, is that in Ceptr, everything is stored as semantic trees at the very base level. So in computing, we're regularly serializing data out to disk or that kind of thing, and then kind of rehydrating it when we instantiate it back into memory. And there's all kinds of places where this happens in various computing processes, like when you write a program, you serialize it out as ASCII, but then in order to actually run the program, it has to interpret all of the characters into symbols and words and tokens and build a whole syntax tree out of the program in order for it to run. And we basically keep it in that form natively. So this applies both to data, which hopefully you can see this. This is just an example of just like a little user profile type of thing, which is stored in a semantic tree where all the parts of it are identified. It also applies to process. So what that means is that we have trees we call run trees, which are the virtual machine's bytecode, sort of, instead of bytecode. And they reduce themselves from a whole tree full of processes, passing the results up the line until all that's left is the result. And this is
Here's a demonstration of
demo.
Using semantic trees as code and data. What you're seeing is a visualization of trees dumped out of the Ceptr system and then rendered in JavaScript using the DC D3 data visualization library in a small little web app that we built for the purpose of this video demonstration. I show you here a run tree. A run tree contains two nodes, the code and the parameters that are being passed to that code. This particular example in the code, what it is intended to do is produce a mailing label from a user profile. So the code consists of a couple concatenation of string elements of the parts of the user profile that's passed in as a parameter. So I'll click on the parameter so you can see that. A user profile is a semantic tree that contains a profile name, a profile address, and an email. Profile name contains a first name and a last name, and a profile address contains street, city, state, zip, and country. When this code runs, it simply is a couple nested concatenations. One of the interesting things about using semantic trees as a code running environment is that it combines the stack and the code in one place, because the trees simply reduce themselves as the code runs in the virtual machine. So I will show you what that looks like. Again, this is just visualizing the dumped out trees that came from the code that was running. So here what you're seeing is the replacement of the parameters in the tree. There you had the first name being concatenated together, the full name being concatenated together. Here you have more replacement of parameters as the tree reduces itself, and more reduction, and finally almost a full reduction down to the resulting mailing label that would be printed out.
Okay. Hopefully this is all visible on your screens. So I'm wondering if we should pause for questions. There are people that are posting things onto the page. Oh look, can we get the Prezi link? And Robert posted it. What currently is the time into the presentation? We're currently 28 minutes into the presentation. Okay, I don't see specific questions about this stuff, so more about the enabling technology, which is the thing we're wrestling with. So let's move forward. So another thing that that makes all of this work is that when we have things stored in semantic trees, one of the things we knew that we were going to need was a generalized parsing engine. If we're going to build a way for protocols to speak to each other and basically have a self-describing protocol stack, we were going to have a generalized parsing engine for parsing different protocols. And what we found in having the semantics built in at the very low level is that ended up being relatively easy to build in a method akin to regular expressions. So we created semtrex, which is our semantic tree regular expression engine or system. And here you can see a semtrex. This is an HTTP request, and it is the structure of an HTTP request. And you can see there's a semtrex expression in the right-hand corner, which is basically saying, starting from the root, the percent means walk, find it anywhere in the tree, to find the HTTP request path segments, and also to find an HTTP request path file. And so you can see the results in red here are what the semtrex expression on the top returns as its match result. And so it ends up being a pretty generalized way that you can match things at any level by their meaning, by their semantics, as well as by values. Regular expressions normally just match by values. And so this allows you to match by either.
So if, for those of you who are coders out there, you know how powerful having regular expressions in your toolkit is. And it's very important because they allow us to search into linear data and find patterns in linear data. We need to have the exact same thing happening at the tree level and have that be a basic built-in function of the whole system. And we have that up and running, as you can see. The example you have here was generated by the testing environment, spitting out the trees into JSON, similar to what you saw before for the animation of the run tree. And this uses the semtrex results to go, and the JavaScript uses the semtrex results to go and highlight these trees.
So in the Hope demo that you saw all kinds of signals being passed around between different receptors. And part of what makes that possible, the way that's actually structured in Ceptr, is with expectation statements. And you can think of these similar to rules in Prolog that kind of fire when different conditions match. So receptors contain series of expectations in this form. On a particular carrier, expect this particular pattern, and if it matches, then do this action. So it's kind of it's like I said, like a Prolog rule that triggers. So it can listen, it can narrow it down to listening only on particular carriers semantically, and then use semantic and value matching for the semtrex pattern, and then perform a series of actions, including typically provide some kind of response. So one of the cool things about this is, that it makes things sort of suitable for parallel processing. Expectation statements can actually be nested, where you use the previous part of the expectation as the carrier, and you can build layers into that. They can trigger a cascade of changes that may trigger other expectation statements by creating new data available on new carriers. And also, this is one of the other kind of cool things, is that listeners are structured in this same way. So one of the ways receptors can relate to each other is they can plant listening requests. Basically, tell me when the weather goes up by 2 degrees, or tell me whatever. You can listen for different types of events. So you can send a receptor a listening request that basically is structured like this. On a particular carrier, when a thing happens, notify me, send me the information. And so that ends up being a really easy way for everything to operate with each other, interface with each other. So one of our goals here was, as I said, to create a self-describing protocol stack, which the basic requirements of which were basically you have to listen on a more generalized carrier. You have to be able to identify a protocol and its semantics. So there's an envelope that basically tells you the meaning of what's coming next, and then the data comes next. But when it tells you that stuff, it has to identify the protocol that it's doing this in, and then have the ability to install a protocol to process the signal if you didn't already have it installed. And so let me give an example of this. Imagine an email message type of thing, where it's a very generalized carrier, where we put all sorts of information in there. We've all run into the situation, I think, where you send somebody a message and you say, I need answers to these 3 questions. And you get a response back where really only one of the questions were answered, and there's sort of some vague ramblings about the other 2, but you didn't get the answers that you need. It seems like it ought to be easy to install a kind of grammar, a kind of protocol on top of email that would, well, not actually on top of SMTP, but in Ceptr, on top of Streamscapes, we could have a grammar that actually lets you define a question as a semantic item, and when you receive questions, it gives you a separate answer box or prompt for each one, and you can't submit your response until there's something in the box for each answer. That's an example of a way that you could have a kind of pluggable grammar where you could send somebody a message and they could receive the message in the more generalized carrier format, realize that it came in a protocol that they don't have, install the protocol, and then be interacting with you inside of the new Q&A protocol that they just installed, and interpret the message they already received through that protocol. We had a really complicated example. It's actually not that complicated in Ceptr. It's really complicated in normal protocol specifications of having an HTTP wrapper around document handling. But I'm afraid that I think that that's going to take too long, and we can come back to that if there's specific questions about this. But it ends up being pretty simple. You define roles of a client and a server, and there's two signal types, a request and a response, and you unwrap the stuff semantically and pass it to a document handler, which retrieves it from the path, retrieves a particular file name from a particular path, and passes it back. So that's not, I'm not saying that does everything that web servers do nowadays, but it's a simple example of a way that a protocol can be used to just wrap something. Take documents from your local machine namespace, put them into an internet shared namespace for making requests. Compository. So imagine if the internet came with a built-in GitHub, but it's not centralized like, you don't go to a particular website controlled by a particular company. It's actually built in at the network layer that there is a code sharing system that is distributed, kind of like a BitTorrent distributed hash table. The compository in Ceptr is what does that, and it is what provides the namespace. Remember in the previous example we said you need to be able to identify protocols? Well, you need a namespace in which they can be identified, in particular an address space for the compositions. They end up with IDs so that you can reference a protocol as being this particular protocol inside of this particular composition in this shared space. As well as it gives you a place to install the things from if you decide that this is a protocol you want to install to handle. And the way that you publish things to that space is you generate a composition ID through a process of having an author and reviewer who's signing off on this actually being what it purports to be, sign the thing, and it generates essentially a UUID for being able to share compositions and have unique namespace for all of the there's some semantic components and protocols that are within them. Oops, we skipped one screen here, which is about the Ceptr network. So one of the weird things is that receptors can actually only interact with other receptors on the same host in which they're running. So to talk to a receptor on another machine, what they do is they talk to a local instance of the Ceptr network receptor, which is itself a distributed hash table type of thing, and so it synchronizes with its other instances to deliver that message. So we end up having the inter-machine communications happening through the Byzantine synchronization algorithms rather than through the front-end protocols. It's a back-end synchronization interface, which addresses some of the issues of the fact that, like the compository, the address space is UUIDs, and you can triangulate with two other members of the network to be able to join the network and be given an address. And so we have an address space that has no relationship to the physical topology. So there has to be a different algorithm for being able to find and generate routes between items or between nodes on the network. So that's just a brief view into the way the Ceptr network works. Yeah. Now, let's try to have this be more interactive. I'm going to switch back to cameras, I guess.
The thing is, I don't think we have a lot of people on live interaction because there's delay on all of it. So
Right.
I have hear someone saying that they're not on live. So I don't know how we're going to be able to do the live interaction with the non-standard Hangout mode with the Hangout on air. Doesn't seem to lend itself to that. But we would be happy to have some questions.
There's 19 people watching on the YouTube's channel, and the delay is a couple of seconds. So there is a delay, but there's not a big deal.
Great. Well, as soon as we get a question, we're happy to answer it.
All right. Next time I should use the Prezi local client instead of a web machine and see if I can share that window more effectively.
Do you have any questions? Farrah, have you been able to see any questions showing up?
No, let's wait a bit so that we can compensate for the delay.
Harlan is saying presentations super helpful. Christopher was saying regarding seeing the thing that seeing the video that it wasn't too bad. And just saying, Adam is saying hi to Gene. Sounds like neurons, Scott Morris is saying.
That's actually not a bad analogy, Scott. There is a lot of neuronness to it.
Okay, other questions? Guess we can say some more things about it. So one of the things is that we are going to try to present tomorrow via WebEx to an MIT webinar. So hopefully that will have not the same technical difficulties we had today. We'll have a different set of technical issues tomorrow. And yeah, we just got a suggestion to talk about some of the next steps that that are.
There is a question from Scott Morris here, and it says, "Can you tell us a bit more about an individual's entity and its connection to the network in terms of its reputation?"
Yeah. So. One of the things you may have noticed from the way that we talked about both the compository and joining the network is that in both cases they happen through kind of a process of triangulation with other parties, basically to lend trust and credibility, because we tie IDs to your network ID is basically what's used to sign everything that you do, and so if you have a bad actor on the network, people that are joining and just spamming the network and stuff like that, we're expecting that there will be reputation currencies, very much like the spam databases for black hole open relay servers, that type of stuff that send mail from spammers off to black holes and that kind of stuff, that's going to probably operate at all sorts of different levels. And even things like whether you would install a protocol or not from the compository may be a function of the reputation of the authors and the reviewer to know that this is something that you can trust. We're intending that there be all kinds of feedback loops of reputation metrics tied to identity here. I'm not sure if that exactly answered the question, and I'm not seeing the place where that question was posted.
In the question and answers, but there is so much that you could probably don't pay attention to both things. There's a question by Harlan. Any interest in a
There's a whole bunch of
JS library running in the browser? There's many questions, actually. You have to run down and see them. There's 2 by Christopher Allen and 1 by Harlan.
Can you delete some of the ones that are no longer useful?
I'm not a moderator. I cannot delete anything. Sorry.
Gotcha. All right. So,
I can read them to you. I cannot even show them on screen, but I can read them to you.
We have Robert asking, to participate in the Ceptr network, what do I need?
Well, what you need is an address to start out with, and that uses our triangulation algorithm to get one. So a lot of systems have this notion that you should just be able to get an address for free, or you get an address because you bought one from some authority who has one. In Ceptr, we have a middle road where you can get an address. Any group of people can get addresses by triangulating themselves into the network, where you're getting an address in some context, but that context is not a centralized context, as it is in the case of an internet address where we have ICANN delegating IP addresses to ISPs who then use them. So basically what you'll need is you'll need somebody who's willing to sign you into their portion of the network and basically vouch for the fact that you're not going to be sending spam or be available to have their reputation dinged if you end up having issues. But that's not a centralized part. Anybody on the network who's willing to set up that pattern of triangulation can do that. You have another question?
I'm placing the questions in our group chat so that you can see them from there and who is placing them as well.
So she mentioned a question from Harlan, which I said done. She mentioned a question from Harlan that I don't see. Here it is. Any interest in JS library running in the browser?
Absolutely. We're very interested in lots of JS libraries. I mean, what you saw with the trees is an example of that. One of the serialization formats that we have for trees, I've written a deserialization from that binary format into JavaScript objects in the browser so that we can be doing most of our UI building in browsers. That seems like the right way to go forward. We want to be, the code itself is written in C for running on the back end and for having as much uptake as possible on different platforms. But for user interface, it feels to us like the best place to go is in the browser and having large components of this stuff running in JavaScript. Another question.
You can see them in our chat. I'm copying and pasting the questions I see, so that you don't have to read through all the questions and comments.
Harlan, okay, Jeff, next up. Christopher Allen, talk more about decentralization.
Okay, why don't you do that, and then I'll talk a little bit about next steps.
Talk more about decentralization. Sure. So one of the ideas is, sort of akin to the, what do they call them in Ethereum, distributed autonomous
CAOs,
organizations. So similar to that kind of thing, if we make a set of agreements for how to interact, whether that's in a currency context or whether that's a contract or whatever it is, we can each take, and we encode them in a receptor, in the way the receptor actually functions, and the types of protocols, types of interactions that we can have around that agreement. We can each take a copy of that receptor with us, and then we know that we can trust our copy. And then the receptors, different copies of the receptors actually synchronize with each other to be able to do the transactions or interactions. So everything is built to be decentralized at a very low level. I don't know if that's
So the other question was, what are next steps in programming? So currently what we've been working on is this low-level stuff of doing the semantic trees and getting semantic trees going so that we have our, in essence, our bit, our character. in regular programming, you have linear bits or really bytes. We have semantic trees as our basic unit. So we've been getting that running, and then having semtrex running on top of that. And then we're creating receptors out of all of these things and the virtual machine that can run them. But our next step is building out that virtual machine, but we also want to be building user interface to be able to visualize this stuff and make it visible like what you were seeing before. So we're kind of going a little bit in tandem with both of those things, but mostly focusing on that low-level stuff. The particular piece that we're working on is the data engine and being able to serialize this data out and have the whole process by which the system boots up and runs and then can close itself down. And then very quickly after that is working on some of the synchronization algorithms that we've worked up to implement them so that we can have multiple instances of receptors and actually do the Byzantine fault tolerance that we know is necessary.
And one of the other things is that we're building toward, so Ceptr is like these underlying protocols, and we're building toward more of a user-ready application that we're calling Streamscapes, which is sort of the universal inbox, the answer to universal inbox. If you have a system that can speak any protocol, that very easily can be programmed for different protocols, and creates a way to be able to pull all of your messages and communications into one space that you can organize and control. So that's the next layer of development after we get all the underlying componentry working. That's the kind of the killer app, the mother app we want to build on top of it.
We like mother app more than killer app.
And then Hayes is pointing out that people can upvote the questions, so that we should look at the top of the list. So
nice idea.
We have Mark Fraser asking if you can create a Darwinian system with this, one that concurrently tests variants of receptors and selects the ones with fewest delays. There's a couple of things built into that question. That this isn't designed to be genetic algorithms, like where you have different things competing and actually evolving themselves. However,
you mean software elements.
Software elements, right. And actually software evolving itself and competing against other variants. It's not intended for that. I suppose it could be possible that eventually that kind of thing could be implemented on here. But when I hear you say selects ones with the fewest delays, I'm assuming that you're speaking more to the routing algorithm and being able to send messages, being able to communicate over it. And yes, that is part of the data that the instance engine, data engine in synchronizing with other instances is collecting information, learning about the physical topology of the network that it's on, and collecting certain information very much a similar way that routers do now. They keep track of everybody near them, and so they know who they have to go through to reach different domains of addresses, but also like what kind of latency delays, what kind of bandwidth and throughput they can expect and through those channels. So
one of the things that does actually speak to this, that we've actually thought about and worked a little bit on how it might work, is not just having the routing happen based on speed, but based on any sort of arbitrary set of conditions. So for example, you may have security conditions which require that your data only go across networks of types that you trust. Or you may have latency requirements for high speed, or actually latency requirements for slow speed, that you want things delivered slowly and around the edges of the network, not traveling on high trunk lines where there's more likelihood to be snooping. And or even based on actual human concerns, like you only want your networks, your data to travel over types of networks that are kinds of people you trust by type, like in your same social group. And because because Ceptr is built in a distributed network, that would actually be possible to do. That your network traffic would hop through routers of certain classes.
So again, questions that are upvoted. Fernanda's sending some in the chat as well. based on the answer to Robert's question earlier, is there one global Ceptr network, or is there each Ceptr network instance, blah, blah, blah. Ceptr is, we're designing Ceptr so that it can function as a global network. Everybody inside Ceptr should be able to talk to anybody else. However, that doesn't give it a monopoly. The idea, in very much the same way that Wikipedia operates on open source software and publishes their databases. So like if somebody could do the job of Wikipedia better than Wikipedia, they theoretically could build a better Wikipedia and go off running and take over that job from them. We are publishing everything we're building already in open source. There's another question from David Armistead about that. There's a link to our GitHub page. If you just search GitHub Ceptr, CEPTR, you should find it. But everything we're building is already open source. We're sharing everything along the way. And the idea is that you could have different competing networks, not because you want people to not because you want to create confusion, but it's just in very much the same way that there's currently like dark nets and things like that. You may want to create a parallel network that only has trusted people in your company and be operating from a different compository and be, that kind of thing, so that it would be essentially a parallel operating network with a parallel set of compositions and stuff, and it could fork and evolve off differently. That would be fine. It wouldn't interfere with Ceptr at all. David Armistead.
Yeah, there's some questions in the text that are not in the quick Q&A, so you can look for them. But I don't know if you already answered to Adam, and there's also one by Jean, and then there is by Noah and David Armistead and Noah Thorpe.
Go to Fair's text that she sent us.
Okay.
I think that would have one.
So, will the code be open source eventually so communities can be assured their system is indeed the only one doing what they think it's doing? Yeah, that's actually one of the things, is that in the compository all the items are signed and checksummed and all that type of stuff, so that you can compare the one that you're running against one in the compository, and you can only trust that receiving that hash, that checksum from somebody you trust, that you don't think has got a corrupted version of it, even though you may pull segments of it from all over the place, like a distributed hash table type database torrent type thing happens. You can make sure the thing that you got in the end is assembled and has integrity, so that you know that it's doing the thing it's supposed to be doing. Noah Thorpe said semtrex reminds him of the argument destructuring in Erlang.
Yes. Yeah. It's also people who are familiar with closure will be familiar with the argument destructuring, and it's actually one of the beautiful things that we've added to semtrex is that, unlike in regular expressions where you sort of refer to the matches with like $1 or $2 and you do it positionally, in semtrex you can do it semantically. So you can create templates very easily with semtrex and create transformations from one type to another type. It's actually quite nice. This kind of answers one of the earlier questions I saw. Why would a developer want to work in Ceptr? What's exciting about it? Well, I'm a developer, and to me one of the things that's really interesting is that it feels like you're coding in Lisp, but even at a more powerful level. Most of us are familiar with how much fun Lisp was to work in. That's because Lisp basically lets you work at the level of trees. And here we get to do the same thing, but the trees understand themselves. They know what they are. So you've got like self-reflective trees in creating your code. And that's kind of cool. It's pretty interesting at that level. I wanted to answer Bruce Long's question as well. He said, I missed the first part, so you may have already answered this. Who writes the protocols? Are they like apps written by programmers? So I think you nailed it in an interesting way. there, Bruce, because typically when we think of protocols, what we think of is a specification for how to interact. And so you specify it in an RFC, which is a flat human document. In Ceptr, a protocol is actually something that's instantiable. So you do describe what the interactions are, but you also can run a protocol directly. So you set up the semtrex, the expectations, and the actions that happen with them, along with the interactions, the steps of the protocol, and you leave the edges available for contact with other aspects of what needs to hook up to that protocol. So they're very much like applications in that sense, but they're I mean, in a sense, it's kind of like an API, but that it's already self-describing. So once you've declared the API, you can actually drop it into your code and use it, and that's part of the whole self-describing protocol stack that we're creating out of this. And the compository ends up being your app store, right? So that there's easy ways to share those apps, to be able to plug them in, you know. Yeah, the quote app store, because you'll be able to pull out a protocol and attach it to your particular set of receptors that you're building as a large composition. Or install a whole receptor. Right. Yeah. I think what that speaks to, just if I may, is that for us at the heart of all of this, it really came out of coming up against some blocks with composable abstractions. In our original work, where we were trying to create large programming systems for the purposes of creating currency systems, we wanted to have this language of these systems that could be hooked together, but that turns out to be really hard. That's why we came and made Ceptr, because you need to have that kind of composability for complex systems. Go ahead. I'm just wondering if we should tell the receptor breakthrough story, or let's answer questions. Okay. Well, this all seems beautiful. I'm concerned about administrative time setting up membrane type particulars. Will there be normal defaults? And, yes, there will certainly be defaults. Hopefully things will be set up with good defaults, so that when you install something from the compository, it installs in a sensible place at a sensible level with sensible default values. That's all. You know, just like people install apps on their phone all the time, and you know, mostly that all goes pretty smoothly because it has its own space and it knows how to interface with the other things it's supposed to interface with. We can't guarantee that all receptors will be written that way, that intelligently, but there's the installation process for a receptor has a phase in which you basically are taking it from this abstract code from the compository, and you're creating a local running instance and binding that to your address space and your data space. And at that time, you can change different configuration options. That's where the defaults would come into play, but you could also use that receptor in some other way than expected, install it in a different space, or hook it up to different things, because you can change some of those things in the installation or instantiation process. But generally speaking, what I envision for this down the road is something much more graphical, where you could do some really complex programming by dragging different types of receptors that have different sort of shapes and hooks on them, where you can only drop this type of receptor in a space that has this type of carrier. So you drag it out onto your workboard, and it'll only land in certain places because you need to be able to have an interface with that type of carrier, and then be able to drag things together and have the defaults connect things together in a kind of simple Lego-like manner, and be able to use them as expected without a lot of programming. And that's actually part of why we wanted to have Mark's demonstration of Hope on early on, because it really gives a flavor of that. And you saw how quickly he was able to create a powerful application that grabbed stuff from APOD and created Google searches at the same time. It's exactly for that kind of reason, and it kind of just worked. Let's see. More questions. Scroll up, because the voted up. Yeah. So why will everyday developers be excited? I think I answered that one. Okay, selected. And done that, and
we can go to the one with Harlan, and then there is others in the text chat that are not being addressed. So answer to Harlan's, and then I'll put you to the other one.
Knowledge, we're at an hour.
Right,
now.
so we should probably... so Harlan asked a question about interplanetary file system and MadeSafe. Do you have an answer to that? I mean, I don't have a lot of familiarity with them. I've looked at MadeSafe, and it seems like there's some possible for synergy, but go ahead.
I haven't really looked at interplanetary, but I have looked at MadeSafe, and from what I know is that the key difference has to do with starting down at the lowest level. It seems like we accomplish all the things that MadeSafe accomplishes, but not on top of the existing layer by being kind of underneath the existing layer and having that be more native capacity that you can then build on. But that's a very approximate statement. Assessment.
Okay.
So we have a question since a while that would be nice to answer, which is, would Ceptr be capable of some blockchain like continual distribution of a trustworthy transaction ledger? Seems like maybe yes.
Ceptr, it does it through the Byzantine distribution of the data engine rather than having like a single signed blockchain. So anybody that is, like if you want to create a currency, you want to join a currency, then you can actually just grab a copy of that currency's receptor, current version, from the compository, install it, create your identity, and you are running your own instance. And that's how you interact with other people through the currency. It's just like if you were installing a wallet. It's just that what you're doing is you're installing a receptor in the currency.
So it's an odd thing, because the way Bitcoin works is it's got this notion of a distributed ledger where everybody sees the same data and the same transactions into that data, and they use that ledger as the understanding of what's real, in some sense. So in Ceptr, you could think of the compository as an example of that, right? Because it's, in a sense, a ledger of all of the compositions that you could install to start running. But we're taking something that looks much more like Ethereum and trying to put that at the lower level where the computational units are what's spread about, and then they have the interaction with each other at a lot of different protocol levels. Where Bitcoin just has one thing that gets stored, we're doing it at a very different level. I don't know if you want to add something onto that.
Well, there's a few things. So if I were to build a Bitcoin alternative in Ceptr, and supposing that I wasn't trying to make it for anonymous money laundering, supposing I was actually trying to make it for community building or something like that, then I would structure it such that everybody had linked transaction chains. And so
the protocol that you create would ensure that.
Yes.
Right.
So in order for me to do a transaction with Eric, I install a copy of the receptor. I interact with my copy, and it notifies Eric that there's a transaction request pending. He accepts it. We both sign that transaction with our keys, which then shows that we both parties accepted the transaction. But when we sign it, we also sign into it the ID linking to our last transaction. So I have a continuous chain of my transactions. Each next one links to the prior, and Eric has a chain of transactions. And we could add a witness, or we could add a couple of different layers of that. But then you actually have that intrinsic data integrity, which shows no tampering has been done at any point in the process. And you could have certain milestones that let you sort of reset an audit point, with some third-party auditor that says, yes, I've verified the transaction chain up to this date, the last 1,000 transactions, and certify it at this current balance, and now you can use that as an audit point moving forward, so that it becomes I don't necessarily need to check the whole ledger if I want to confirm your balance. I can check your chain.
But I think one of the big differences between the Bitcoin approach and the Ceptr approach is that and especially if you think about it in terms of Ethereum and some of the other interesting things that are happening built on top of Bitcoin, is that they start with a distributed ledger and build on top of that. We kind of start the other way around with distributed process, distributed protocols, distributed computing, and then we build intrinsic data integrity and ledgers and shared consensual reality on top of that. So it's a kind of inversion of approach, which I think actually will get us computation in this distributed fashion much more efficiently than what will happen when you try to do mining to be the fuel for your blockchain. It seems, I mean, although the Ethereum people are really doing some interesting things, and I'm really very excited about it, it seems to us like a flip way of doing it. Let's see, next question.
Oh, did we? What's the plan for time, history, context? I see a trend in computing toward persistent data structures.
Just select.
Oh, sorry. Yes. Points of time, branches, sharing subtrees.
This is a really good question, Lewis. The question about time and history. Well, one of the things that I would say is that one of the places that we have thought about this is in versioning, and also at the very low level in our data engine, how we store data and we log data, and we keep multiple histories, multiple versions of reality. It doesn't quite answer your question, but that's something that we're really keen on. So some versions of persistence, things like the blockchain, and also things like the Paxos method of doing Byzantine fault tolerance or distributed consensus, they tend to have the approach of let's figure out what the shared reality is that we have, and then only advance forward if we have that shared reality. The Ceptr approach is to allow for multiple realities that can merge.
Or fail to merge.
Or fail to merge, because actually then that's called forking. And that's actually a really important feature to be able to build in at the lowest level. But you're actually asking about time and history, and or time, which is different maybe than history, because history has to do with logging. Time has to do with the shared consensus around when is now. And that's actually an open problem for us, where we've had some ideas about how to do that and have looked into NNTP and how they do that. And we'll probably be using something like that. I don't know if you have anything to add. That's a little bit of hand-waving answer, honestly.
I want to say something about the versioning, because if you publish something to the compository, the very first branch point from its root identifier is actually the version. The reason for this being we don't want you to lose continuity of identity of something just because it's been updated. So you want to continue to use the same address to find that thing in the compository, but now the version number becomes a part of the sub-address. You can address down a tree from there, and so when you go to that address, by default, you would always get the most recent version. But if for some reason you needed to maintain backward compatibility or you needed to install an older version or something like that, you could address that explicitly and install that version for compatibility with something else that hasn't been updated. What we're also trying to do in doing that is build in the ability for rapid evolution and easy deprecation of things, which right now that seems challenging for us as a widespread community. So we have some reputation currencies. How things keep disappearing from here that I saw a minute ago.
Maybe.
Has your work with Ceptr informed your thinking with MetaCurrency? Let's do this one real quick.
Go ahead.
So has your work with Ceptr informed your thinking with MetaCurrency? What has Ceptr empowered currency constellations. Yeah, as we said at the very beginning, our work with MetaCurrency is part of what sent us down this path. When we started looking at, to do a transaction between the two of us via PayPal, right, which is supposedly peer-to-peer transaction platform, right? Like it allows people with a email address to send anybody else with an email address. We have to go through like 9 different centralized steps in terms of getting an IP address, which really is controlled by a central authority, even though they're delegated out to a handful of ISPs, and using domain names for namespaces and emails for, all these different things, then using a centrally controlled currency and using a centrally controlled transaction engine in PayPal, where we can't represent our own reality about these things at all. There just was so many layers that weren't meeting our requirements of openness, which was basically about unenclosability, that nobody can enclose it and take control of it. And like if you think about it, that's also part of what the Bitcoin blockchain is trying to accomplish, except for the 51% problem, right? If you you control a majority of it, you start to be able to do things that you don't want people to be able to do. But we were taking a different approach to have it be fully distributed and have, as Eric said, different realities that then reconcile. Because I do a transaction immediately through my instance of it, and then it starts synchronizing with other things to bring them up to speed. And if Eric rejects that transaction, now I have to reconcile. Maybe my system is pretty smart and just automatically goes okay and undoes that transaction or voids that transaction because it was rejected. But so it doesn't have to be complicated from a user side. It just Ceptr allows for my system to be in a state of I've authorized this transaction, even though Eric's system hasn't received it yet, and is through the synchronization process always dealing with those multiple realities, and that's.
So I mean, to answer the question, what has Ceptr empowered in this view? One of the ways you can look at that is that if you think about real reality, where humans interact with each other and they say, I want to do X, and you talk to a person, and another person says, I want to do Y, and you negotiate and you have a conversation and you create a cultural protocol. In a sense, what we're trying to do is replicate that possibility in a decentralized way and in a way where all of us can create those protocols, that they don't get reestablished to the, they don't get funneled up to pyramidal power structures that are the only ones empowered to do that. And so it feels to us like that might be possible with what we're building.
And the fundamental composability of everything talking to each other is what enables currency constellations, what enables one currency to listen for some dimension inside of another currency and be linked to interoperate that way. I'm just gonna, we already said that one. Okay. So couldn't reputation currencies eventually get created to do the triangulation vouching? Oh, sorry. Good point. Would this then remove all hurdles of entry into the network? Yeah, that's what we were trying to talk about. I mean, basically, it's not about removing all hurdles of entry. We don't want to remove all hurdles of entry, because if you get blacklisted from the network if you get onto one of these bad lists because of bad behavior, you don't want there to be no cost to generate another ID. You actually want, which then you're going to do a bunch of bad behavior and we have to blacklist and blah, blah, blah. You actually have to have other people who are willing to vouch you into the network and may risk their reputation declining by your behavior such that they start getting blacklisted out of the network.
But I think that answer is yes, as a result of that. That's how it works. I mean, what makes you be able to use a reputation currency to get onto the network is because you actually have an understanding of how a player behaves, right, in a particular context. And so that it's also not a global reputation, it's a reputation in a context where it makes sense to say, no, you shouldn't participate in this context. In another context, that behavior may be perfectly fine.
We have a question from Noah Thorpe, too, over here. How is Ceptr similar to extensible data interchange, XDI? It's interesting you asked that. I don't think we talked about that, Noah, on the when we spoke before, but I feel like XDI has gotten a lot of things right and has been kind of undervalued. And we were inspired in a lot of ways by things that they did, including things about versioning and language options and linked contracts and different stuff like that. And so a lot of what has found its way into Ceptr has been in part inspired by XDI, although our implementation of it is different because they're coming from a fundamentally distributed system, and they are coming from a system of brokers, basically, where you have a host that is hosting your stuff. So it's sort of semi-centralized or semi-decentralized because most people aren't hosting themselves. They have some broker that is hosting the information, although some people could be their own brokers.
Yeah, but they've done a lot of things right in terms of using the way they use some of the URLs and using numbers for creating identifiers and names that resolve some of the permanent names and numbers. So we are definitely inspired by their work. Yeah. But again, where we came to this from this place of trying to create a kind of composability at a very, very deep low level in the computational stack, which is what led us to the semantic trees, that's why what you saw in the presentation. Because I think you could go back and rebuild a bunch of the things that they've done in the URI paths and in these forms using semantic trees and semtrex that would, I think, solve a lot of problems. I haven't thought about that recently, but it'd be interesting to go back and look at that.
I'm feeling like we should wrap up soon.
Yep.
There's a question from Harlan about, here, I'll select it, the friendliness of certain distributed systems from a data archaeology perspective.
Could Ceptr data be read by an archaeologist in 1,000,000 years? Interesting question.
Yeah, I have no idea about that one.
It seems like because we've got semantic trees, if it can be read, like there's the physical constraint of are the hard drives or whatever chips are around. If the media is still there, then there's this other question of can it be understood? Can you make any sense out of it? And it seems like if all of your data comes with in this web of linked semantic
identifiers
and structural identifiers that help you actually understand it, it may be more friendly to archaeologists than just plain old bits, which is what our current system seems to be built out of. I don't know if that's really an answer to your question, but
that's a fun thought.
Yeah, it's very neat.
All right, cool. Well, we have some various thumbs ups and things, and sorry we didn't have Mark on the call, and we didn't. This is my first time hosting a Hangout. I mentioned the disaster at the beginning, and so we probably should have figured out how to have more people in the green room rather than just use the Q&A channel. But appreciate you guys giving us a chance to go through this before presenting to MIT tomorrow.
Yeah.
That call is also open as far as I know.
So if you want to try to see a better version of the presentation, if we don't get it better, then I think we have something to talk about there.
Yes, we do.
Give us a holler. And if you have feedback on the presentation itself, we should. Did the Prezi link get up? Because maybe we could
Robert posted the Prezi link on the event page, and we can post the WebEx stuff
on the event page as well.
The event page as well.
So if you want to see us give it another try tomorrow, and if you have any feedback on what would be more helpful, what would be less helpful, etc., please give it to us. And
yeah, you can post on the event page or email or whatever if you have some feedback about how this should be done better tomorrow.
One of our senses in setting this up was to have a friendly audience who would be willing to watch us fail, and I think we've had exactly that, and I'm very grateful to you all for providing that and living into our ideas. All right, thank you very much.
Thank you, Fernanda, for helping with the infrastructure. She's actually in the Hangout here. Okay.
Great. Thank you very much. Take care, all. Bye.